All right, guys, we're going to talk about electric motors here, and I've got an electric motor right here. I want you to take a look at this. See, I've got a battery here, this battery. This battery is touching some aluminum foil. So when I touch the aluminum foil to both sides of the battery, electricity runs and touches these paper clips. Then the electricity runs through, it touches right here. See where this is metal? Right? The aluminum foil is touching the paper clip, which is touching the wire. So therefore, a current runs through the coil. And we know that as a current runs through a piece of wire, it creates a magnetic field. So now we have a strong magnetic field through the coil, right? And then, obviously, the current continues, touches this paper clip, and then back to the battery. Now, under this coil, there's a little magnet. See that magnet there? So if the coil is creating a magnetic field that is the same magnetic field as this magnet, then if you have two norths against each other, they're going to have to repel. So if we did this and we turn the electricity on, if there was a north side going down through the coil and the magnet was a north, then the coil would have to flip over. And then when it flipped over to here, it would get stuck because this side of the coil would now be a south. Do you agree with that? So what we did was, if you look really closely here on the wire, there's some purple marker. And the purple marker doesn't conduct electricity. So every time we flip around where the coil should get stuck, the electricity's cut off for a second and it keeps going. Let's see if we can get this thing to work. So there's an electric motor. That's how an electric motor works. Every time the coil comes around, it repels the magnet, or the magnet repels the coil, however you want to think about it. I just balanced this one a little bit better, see if I can get it work better. And then every time we're in the wrong position, whoa, the thing went out super fast, didn't it? Every time we're in the wrong position, the current is cut off by the purple marker. Now this one's obviously sliding to the side and making itself stop, but I think you get the idea. Let's look at a bigger picture of this. Now here's basically the same electric motor, and to make it make sense to you, we're looking at the coil from the side. So remember, when the current's running through the coil, we have a north or a south magnet coming out of that end. So we're looking at this coil from the side and watching it spin from the side, okay? Now this picture, this motor is twice as good as that motor because now you have two different magnets or two different poles on each side of the coil. Now I'm going to pause this in a minute. As this comes around, as the coil spins around, right, there's a current running through the coil. See, this says to battery. So as the current runs through the coil, it touches the green and the red touch. Now, here's a wire, and this is what we would call these things in real life. This red would be called the brush. And it would be like a little metal brush that could touch this little piece of metal that's connected to the wire in the coil. This piece of metal that's connected to the wire in the coil is called the commutator. So this whole piece in the middle, the green piece, is called the commutator. The red pieces are called the brushes. So as the battery pushes electricity to the brushes touch the commutator, and now the coil has an electric current running through it. This electric current is creating a magnetic field. Out of this side of the coil is the north side of the magnetic field, and out of this side of the coil is the south. So every time the coil is in this position, the north and the north push on each other, the south and the south push on each other and make this thing flip around. Well, since it flips around, you would think, oh, well, when it flips around, now it's going to get stuck. Because now your coil, the north side of your coil will be over here, and it will be attracted to the south side of this magnet, and it will stop. But that doesn't happen. Here's why it doesn't happen. The commutator has a break in it. See how the commutator, the green piece, isn't solid? And notice the brushes don't move. So every time the coil spins around, the brush is touching the side of the commutator, or the wire in the coil, that will keep the coil creating a magnetic field that's always north on this side and always south on this side. So the two magnetic fields are always repelling each other. This motor will keep spinning and spinning until the battery goes dead, because the magnetic field produced by the coil will always repel this north side of the magnet. It never ever turns around and becomes north on this side, because the commutator has a gap in it, and the brushes are only touching the sides of the commutator, or the wires, when they come around, that keep the coil charged like that. So we're always repelling. That is a basic DC electric motor. Now I'm going to try to draw you a picture here real quick. If we have a magnet, let's now draw a magnet that's going to spin. Okay? I'm going to drill a hole in the middle of this magnet, and that's going to allow the magnet to rotate in a circle. So the magnet is going to be able to spin like this. Now normally we just spin the wire, but I'm going to draw the magnet spinning because it's a little easier to teach that way. As the magnet spins, we could put a coil of wire right here, and we could have the magnet go past the coil. All right? Now, as the south end of the magnet goes by this coil, it will create a current in the coil. That's electrical induction, or that's electromagnetic induction, and that's what happens. This magnetic field permeates free space. It goes near the wire. The magnetic field creates a current in the wire. So let's say as the south comes down here, the current will move in that direction. Well, what would happen when the opposite side of the magnet came and swung down past the wire? What would happen if the north end, or the opposite end of the magnet, moved past the wire now? Yep, it will create a current that would now move in the opposite direction. Does that make sense? If we spin this magnet at just the right speed, we can create an AC current with 60 hertz. 60 hertz is the frequency with which the current moves back and forth. That's the frequency of the current moving back and forth. So if the north came down, the current goes that way, and then the south comes around, the current goes the other way. Every time that switches, that's a hertz. So if we spun this magnet around 60 times per second, we would make the current go back and forth with a frequency of 60 hertz. AC means alternating current. The current here alternates back and forth. So if we spin this motor and we make a current go back and forth, if we are the people that are spinning, say we have a handle on it, and we spin this handle and we make the magnet move, then this would be called a generator, because you would be generating the electricity as you spun the magnet. Now, if we did this the other way, if we had a battery here, right? If we had a battery here, or not a battery, excuse me, we'd need AC. If we had plugged this into the wall, we plugged this into our wall outlet, and we made the current go back and forth through these wires, then that could turn around and make the magnet spin. That would be a motor. So if you hook electricity up to the coil and make the magnet spin, then that's a motor. If you grab the magnet and you spin it with your hand and you create electricity, that's called a generator.